Right, so I'm going to explain a basic method of using key pairs to be able to create a shared key. Okay, so just a quick background on what elliptic curve cryptography actually looks like. Okay, so with elliptic curve, what we have is our elliptic curve, which is defined by some mathematical equation, and then we have a point on the elliptic curve. We then generate a private key, so that's typically a 256-bit key that we use as a random number. And then what we do is we take the gradient, which is defined by this private key, and then project up with a line until we find our public key. So our public key is equal to our private key multiplied by g. Okay, and g is a known value. The public key is also known, but the private key is kept secret. And even by knowing g and the public key, it is not computationally possible within a reasonable time to work out what the gradient is here. Okay, so in normal elliptic curve cryptography, we just use one curve, g, defined by g value. But in our crypto key pairs for BN curves, we use two elliptic curves. Okay, we map one as G2 and the other one as G1. And then there is a mapping between the two curves. So in this case, when we look at our key that we've generated, we can see that we have 2 points. Okay, and that is our pair. So we end up with a pairing. So one comes from G1 and the other one will come from G2. Okay, so let's look at a practical example. So in this case, Bob, Alice and Carol want to generate a shared secret key, and they only want to communicate their values once. So in this case, Bob, Alice and Eve each generate their own private key. Okay, that's B, A and C. Then they create their public key pairs using G1 and G2. So they all agree to G1 and G2. So Bob finds this one, PB, which is based on G1, and QB. Same again, Alice does her calculations, and Carol does hers. Okay, all using the same G1 and G2 value, but they obviously have different private keys. Then they exchange their values. So Carol passes PC and Alice passes QA. So that's based on the Q2, the other one is based on Q1. So that provides us our pair that we require. Okay, so they end then going together to create our pairing, and then after that we multiply by the private key and we should end up with the same key. So same again happens with Alice. Alice will get, say, Bob's PB key, and Carol will send her QC key. She will multiply by the A value, and they'll all end up with the same secret key. So even though Eve is listening to the communications, she cannot determine what the shared key is for Bob, Alice and Carol. Okay, so here's some outline code which implements this. So here we are, and we have our random values between 0 and G2, random. And then after this, we calculate the public key values. So in this case, we're calculating Alice's values by multiplying A with our G1 and our G2. After this, we'll exchange the values, and then we calculate our first key, which is taking QC, and PB, so that's from Carol and Bob, and then we're multiplying it. The exponential and discrete logs is equivalent to multiplying, so that's the A value that we take here, and then that calculates that key. We then do the same for the other keys, and if they all tie up, then we successfully generate the key. And even though Eve is listening, she can't determine the shared key just by listening to the values that have been passed. So here's an example of a key generation. So there's our A, 256-bit random number. Here is Alice's public keys. Okay, so we can see it's a key pair. And then what we'll do is we'll pass the values and then end up with the same key. So let's have a look at an example. Okay, so it'll take a few seconds to generate it, but the code we're using is something like this. Okay, so we'll just generate it. So it's just going to take a few seconds to generate. It's going to generate our A, B, and C random values, and then pass them, and hopefully we'll end up with the same shared key. Okay, so there we are, and the keys actually work. Okay, so in this way we can actually pass values using our crypto pairs and end up with the same secret key.